Hi everyone, I hope that you're all doing well. In this video, I want to show you a proof of the binomial theorem and then a natural extension of that theorem to one of its very many uses, which is a proof of the derivative rule in single variable calculus. So let's start by talking about what the binomial theorem aims at. And what it aims at is to find some kind of generalization for what x plus y to the n should result in. And so you might remember from high school math that in the simple case of x plus y squared, this type of binomial expansion is oftentimes referred to as foiling. And what that tells us is that when we do this expansion out, we apply the distribution rule in two ways. So we go x to x, which is the first, x to y here, which is the outer, y to x here, which is the inner, and y to y here, which is the last. And there's another method that's more commonly taught recently known as the box and diamond method or something like that. I'm not familiar with that because I learned the FOIL method when I was a kid, and then I learned the binomial theorem when I was older, so I don't know any like new heuristics, but you may be familiar with the box and diamond. What I'm going to show you in this video, though, is that the best thing is to just learn the binomial theorem and then not need to remember this. So that's what we're referring to here. We're trying to find a generalization of this type of pattern. And it turns out that there's a very elegant one. And so what you might think is, well, why does this work in the first place? Why does this distribution work out in the way that it does? And the logic is this. So if we imagine multiplication as trying to figure out, say, the area of some field here, you can just imagine that this is a farmer's field or something. I know I haven't drawn it exactly rectangularly, but let's suppose that we imagine the field is being partitioned in this way. And let's say that this is the measurement x, and we'll denote these with subscripts x1 and y1 and so on. And then we'll come up here and do x2. And then we'll have over here y2 and over here y1. And so if we imagine the process, and note here that x1 and x2 and y1 and y2 here are the same, right? So you can kind of see that we've swept out this area here and this area here, and these are meant to be the same size. So how would you find the area of the entire field? Well, it's pretty visually obvious that you would just find this here, and I won't use the subscripts anymore because these are the same thing. And so this is kind of a visual justification for the distribution rule. In general, what you can think is that to find the area of a field like this, you would basically go and say you start with the length of one part of the field here, then you take it to the corresponding subsets that make up the width, or however you want to think about it, the second length. And then you do that just for as many lengths as there are for the entire field. And so that's a nice kind of intuition for why this works. And then what we want to do is just see how that might generalize. So let's say that we are now thinking of the case of x plus y to the third. And I'm not drawing this to scale, or it's not necessarily going with the previous figure, so just leave this as kind of a separate example in your mind. So let's say we now have some previous result from the binomial expansion of order 2. And so we know that that's generically going to look like this. And what I want you to do is, instead of thinking about, I'm not drawing these exactly to scale, instead of thinking about these with the gathering of terms in the traditional way that you've been taught to do it, so instead of x squared plus 2xy plus y squared, leave ungathered. And you'll see why in a second. It's because it helps us figure out the general pattern. So we now have this here. And now we partition. So that's the length. We'll partition the width. Let's make this exactly straight. into an x term and a y term. And so now again, if we imagine what's going on here, we're going to do the same thing. So we match these two terms here, 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 and then we do the same thing, and I won't draw that out because it's going to get messy. And you can see that that's the general procedure. So how would we write that? Well, we would write that like this. And then we just distribute. I'll show that here. So we come here, and then here, and so on. And so if you then think about it, what we're doing is we're matching basically every distinct term that could possibly exist, or every distinct possible combination of terms. And that becomes evident if you write in the subscripts here. So this is x3, this is y3, this is x1 and x2, this is x1 and y2, this is x2 and y1, and this is y1 and y2. So we formed the four initial possible combinations from our expansion of x plus y squared. And again, just to show how that kind of worked, I'll put it back in the subscripts here. We found x1 and x2, we found x1 and y2, we found y1 and x2, and we found y1 and y2. And so what we're doing when we do this expansion is we're matching all of the distinct terms. And so if we go to higher powers, so we have x plus y cubed, what that really is just x plus y times x plus y squared, of course. Right? If you multiply these two things together, then you could re-express that as x plus y cubed. And so then what that means is that if we found a simple visual intuition for how to come up with x plus y squared, and we found that we matched all of the distinct terms, then what we're doing, if we add on x plus y with the third degree here, then we're just iterating that same procedure. And so what we end up doing is just matching every distinct possible combination of terms. So then if you think about it, what happened in this first case, we had 4 possible terms. Then in this case, we're multiplying all of those four terms by 2 different elements. So here we have 8 possible terms, 8 terms. And you can see visually again, here's 1, 2, 3, 4, 5, 6, 7, 8. Now there's going to be repeats, but that doesn't mean that those aren't separable. It just means that we can add them up, but they're unique terms basically. And again, if you put the subscripts in, you'll see that the subscripts on repeated terms aren't the same. And so then we can generalize this. And so we can say, generally speaking, x plus y to the n has 2n terms. And then we only want to think about the pattern. So if we think about it, if we have this general pattern where we've got x plus y 1 times x plus y 2 times ellipsis x plus y, to the third, but to the n. And then you think about, well, what's the total possible set of patterns? Well, you're going to have some extreme forms and some mixes. So let's write that out here. So our extreme form is just going to be x to some power. And you can probably tell that it can't be higher than the power of n. So we'll say that that's true. And then we can probably guess, well, I can find a way to get all x's and then one y. So there's going to be x to the n minus 1, y1. And then we can figure out that this pattern is going to extend like this. So we can just see logically that this has to be the case, that it's got to be something like this. So now the task is to just figure out what the number of the coefficients are in front of these, because there are these coefficients that I haven't written in, a1, a2, an here. So how do we find those? Well, if we think about the process, we've got here n sort of buckets where bucket is defined to be an x plus y term. So what that means is that when we have these buckets, we can think about, well, in front of each term in the expansion, we put the number of ways to choose. Basically, well, so what do we want to think about here? What is the things that we're choosing? We're choosing combinations of x and y. And you might remember that combinations actually have a formal definition that we'll come to in a second, but I just want to briefly show you that these can be understood as combinations. So we'll come back to what I mean by combinations exactly. Don't worry if you haven't heard that term, or you've probably heard it, but don't worry if that's not calling to mind something very specific. So here's how the process works. We're basically saying we pick, say, k x's from n buckets. So we have basically up here, we have n opportunities to pick k x's. So that can be expressed as n choose k. And let me show you briefly what n choose k means. So you can think about basically combinations and permutations as they're known in this setup here. So think about this matrix here. And you can think about basically a situation where you want to choose some items from a set. Some of the items or some of the situations order matters. So you care if you say pick a set of billiard balls from a larger set and you want to know like, is there a distinction between picking 3, 4, 5 and 5, 4, 3? That would be the case where order matters. And then in some cases, order does not matter, right? And then you have another situation. I don't know why I'm changing colors here, but we can say replacement and no replace. And what that means is that when you pick some items, do you put them back in the set to choose from, or do you not? So let's think about a kind of classic example here. Let's say that we have a situation where we're just going to focus on no replacement, since that's often more useful for a lot of applications. So what would it mean if we think about the number of ways to pick, let's say, task, find ways to pick 3 billiard balls from, a set of 15, or 16 I think there are actually. So let's think about how we might do that. And that's going to go in this bucket here, because that's a case where we're not replacing them, because once we pick a billiard ball from a set, it's no longer available to choose just by the rules of physics. But there's a lot of situations where we could, in theory, put it back, but just won't want to. And then order matters here because, and put them in order just by fiat. And then we'll talk about the unordered case. So the idea is, well, how many options do you have at the first moment? You have 16. Then if you don't put it back, how many options do you have at the second moment? You have 15. And then if you don't put it back, you then have 14 options at the third moment. And you can see, you might want to draw this out here, that this might correspond to picking 5, 4, 3. That's one way that this could happen. So like, let's say we draw our branch here, and I'll draw these other branches, and we're not going to have time to fill them in. It would actually, if you do the math, take a very, very long time, but you can kind of do, okay, that goes to 4 like this, and then, okay, that goes to 3 like that, and you can imagine that these are all other options here. And then note that there would be a separate branch, for instance, that would result in 4, 5, 3, etc. So the correct way to count this is to say we have 16 options the first time, 15 the second, and 14 the third. So that's our solution. And if you want to think about a clever way to write that, really what this is this is n factorial, where factorial means basically you just multiply together all of the numbers from n down to 1, or just really implicitly 2, because the 1 at the end is somewhat perfunctory unless you're getting really deep into the theory of factorials. And then we want to divide it, however, because we don't want 16 times 15 times 14 times 13, etc. We just want 16 times 15 times 14. So a clever way to express that is to just write, well, in the denominator, divide by n minus k factorial. And the reason for that is that that's going to say, okay, so I want to put in the denominator, in this case, 16 times 15 times 14. I want to put in the denominator now 13 times 12 times 11. And you can see that this will actually be 13 times 12. And note that these are all going to cancel. And so what this is telling us is basically in the denominator, start the index at whatever the first number is that's smaller than the number of items we want to choose subtracted from the total. And that's just a clever way to arrange this. Now, finally, to get, so this is n factorial over n minus k factorial. To get the formula for combinations, what you want to do is then think about, well, we've overcounted if we're only concerned about the combinations. For example, the set 5, 4, 3 is not the same as the set 4, 5, 3 when you care about the permutations, but when you care about the combinations or the groups, it is the same group. So you then want to think about, well, how many ways do I overcount when I count, say, 5, 4, 3 and 3, 4, 5 and etc. separately? And you overcount by a factor that is exactly the number of ways you can order those k items. And so how many ways can we order an entire set of k items? Let's use the formula we just found. So how many ways to order k items? Hopefully intuitively you can just see that it's k, but also notice that if we put it into our formula, so we'll now say, we'll just replace k, and then here in the denominator, we've got k is the number of items, and then we're selecting all k of them. And then what this gives is k factorial over 0 factorial. But it turns out that by definition, and I don't have time to get into this here, 0 factorial equals 1, somewhat magically. So there's not time to go into that here, but you can also just say, well, okay, that's the rule, and my intuition confirms. So the number of ways you can order k items is k factorial. So finally then, to undo the overcount, if we use n factorial over n minus k factorial to count how many groups, there are of size k in I should call this distinct groups, a set of n items, divide by k factorial. I'll put this in parentheses to show that that's not an exclamation mark in the normal sense. That's the factorial operator. So that means that we can write this like the following. Which is often written in this fashion here. And that tells us that basically the number of ways we can pick unique groups of size k from a set of n items comes from finding out how many ways we can arrange k items from a set of n, where we count the billiard balls 3, 4, 5 in order as different from the billiard balls 4, 5, 3 in order. And then we divide out by k factorial, or in other words, we divide out by the number of distinct arrangements of those k items. And I want you to notice a very important property here that I'll probably use in this video in a second. Notice that n choose k is equal to n choose n minus k. And I'll show that briefly. So just think about coming down here. Algebraically, it's simple. So we just swap out, see here we've got the k, so swap out n minus k. And then here, okay, so we're saying replace k with n minus k. So you have n minus k. Now you can see here that when we distribute, these n's are going to go away, and then these two negative signs team up and to form a positive. And so this just ends up becoming, well, so here we've got n minus and then plus k. So this becomes, so this is the same thing. The order in the denominator doesn't matter because multiplication is commutative. And intuitively, that should make a certain amount of sense, right? So if you think about, okay, when I pick a distinct group of 3 billiard balls, that is also a way of forming a distinct group of 13 billiard balls. So picking the set 5, 4, 3 also means picking the set 1, 2, and then 6 through 16, right? So there's no two ways around it. When you pick a set of k items, you're also, if you think about it, like just imagine having all the items in, like on top of the billiards table. When you parcel out 3 of them to the left, you're also parceling out 13 of them to the right. So this also makes a lot of intuitive sense. So then if we come back to the binomial theorem here, that means that it's a really nice way to count up. If I've got those buckets, let's just come back up here. I don't want to redraw this. If I think about these basically as buckets, right? So I'm going to each bucket and I'm selecting an X or I'm selecting a Y. Then when I get to each bucket, I pick basically, right? So I've got n buckets, and to get k x's, I have basically n choose k ways of picking them, right? So there's many different ways I could get, say, the same number of x's from n buckets, and n choose k is just a way to count that. So then what we get here is that x plus y to the n is equal to the sum, we'll say from k equals 0 to n, if n choose k, and I'm going to write this in the conventional way that uses the same property that I just mentioned, which is that n choose k is the same as n choose n minus k. So you'll see here that it doesn't make a difference, but we're going to write this somewhat counterintuitively, maybe at first, as this is here, x to the n minus k, y to the k. And the reason for that is that we, in this way, start with the x power first, which is just conventional. But notice here that it really doesn't make a difference because that, and you might also worry too, like, well, wait, we said n choose k is the way of choosing k x's, but we also have to multiply it by, n minus k y's. But remember before that because the binomial coefficient, as it's often called, which is this thing up here, because of this equality here, we don't have to worry about that. The correct multiplication or scaling factor for the x term is the correct scaling factor for the y term. So we can see what that would look like. Let's just start with something simple. So we would say, okay, so n choose 0 times x to the n times y to the 0. And let's just write out the first two terms. N choose 1 times x to the n minus 1, y to the 1, plus etc. So then what we can say here is, okay, so how many ways can we choose 0 items from a set of n? Well, there's only one way. Don't pick that item. So that just becomes 1 times x to the n, and then y to the 0 evaluates to 1. Then the next way, how many ways can we choose one item from a set of n? Again, that's intuitive. You can plug these into the formula, and I encourage you to do it, but hopefully it's just intuitive. There's exactly n ways. So we say n, x to the n minus 1, y. And then we go on, and then the coefficients get somewhat more complicated, but notice that these two are always going to be the same. And it's really more important to just know the general formula in order to solve this problem. So now let's come back to the definition of a derivative. So let's show how we can use this to prove the power rule. So let's write out a generic function taken to some power. So we'll let f of x equal x to the n. And then what we'll do is say that we want to formally define the derivative as follows. So we say that it is equal to the limit as h goes to 0 of f of x plus h minus f of x, which you can think of as basically being y2 minus y1 over x plus h minus x, which you can think of as basically being x2 minus x1. So what this tells us to do is look for something that looks a lot like the slope equation, except we are looking at it in a situation where the x distance traveled is becoming arbitrarily small. So let's plug that in more specifically to the formula x to the n. So we'll say that that's equal to here, the limit as h goes to 0, of x plus h to the n minus x to the n over, and we can just simplify here, this is just going to become h. So there's a problem here, which is that if we wanted to simply try, say, plugging in h, which would be one strategy, we're going to run into the issue that h cannot be 0 in this way of expressing it, because then we get an undefined expression. So what we want to do is do the expansion implied in x plus h to the n, and that was the purpose of our discussion of the binomial theorem, at least in this context, although it's very generally useful. So let's go ahead and think about how we would expand this out. And you'll note that we first, of course, as noted above here, change the pen color here, we noted above that these two terms were going to be especially important in this particular context, and we'll see why in a second. So note that our first term is going to be x to the n. Our second term is going to be n to the x to the n minus 1 y. Oops, sorry, here that's h. And we can write out a couple more terms here. So our next one is going to be n choose 2. So we're going to say basically find the number of ways that you can choose all but 2 of the items to be x. And this is going to be here 2. Then n choose 3. Again, that's the number of ways we can choose all but 3 of the items to be x. And then we'll put in an ellipse here. And then we'll say that we end up with the very end of things. We can just kind of simplify, and you can see that the point is we're going to have h's all over the place. So the last one here is just h to the n. So when we do all that and recall that all of that is over h, what do we notice? Oh, and by the way, there's an x to the n on the end that we forgot that was from up here. So what we would notice here is that these two things cancel. And then everything has an h in it that remains. But it's only in one case that h is going to fully disappear. So this involves an h here, this involves an h here, this involves an h here, many h's in the last case. So we're going to have something where we have, in simplified form, we have n times x to the n minus 1 plus many terms with h as a factor. So the limit as h goes to 0 then is just equal to n times x to the n minus 1. And so that's how we can prove the power rule using the binomial theorem.